Hello and welcome to image analysis using Python. My name is Mukaila Wasiu. In this video, I'm going to show you how a program written in Python can determine which image is a cropped version of an original image and which image is a subset of an original image. So invariably and in summary, this program is going to tell you how you can determine a subset of an image through image analysis using the Python programming language. Image analysis is a sort of data analysis, and images are data in their essence. An image consists of pixels, and pixels consist of data represented by the color of the pixel and the pixel's transparency. Pixels are arranged in rows and columns, and when centered properly, they represent an image. So when we are given two images, a program can determine if one image is a subset of the other. The image will be in JPEG file, and resolution and bit depth of the image will be the same. I have provided a set of images and expect the program to return a table showing which images are cropped version of the others. So if you look at my code here, let me tweak this to the side. I have a folder containing images here. If I open it one by one, see that this is a crown image used in chess. Then this is another image. This is another image. I have image of a beach. I also have an image of the Caribbean. This is the Caribbean island. I have the image of Dalton, John Dalton, which is used for atomic theory. I have the image of the Statue of Liberty in New York, United States. And I have an image of a pigeon, which is going to load now. There's a pigeon. This is the cropped version of the pigeon, which is going to load now. You can see it has been cropped. And I have the image of a couple on a wedding day. This is the image. So my code is going to run in this main Python file. I call it main.py. So to solve this problem, I've used standard Python modules and packages. I use the OS module to access the operating system. This is one in line 1. So the OS module is used to access the operating system, and this is used to find files in directory and generate the path to the files. From the math module, I'm going to use the square root method, which is the square root function, to calculate the RMS value. The RMS value is the root mean square value of an image. For the histograms, the time module is going to be used to record the time that elapsed during the program execution. And the Q module is going to be used to maintain a list of all the pairs of images to be analyzed, because we need to put them in a list. Finally, I'm going to use the tkinter module with the ttk package to build a customized graphical user interface GUI. The third-party Python packages that I use include the NumPy, which is this. The NumPy is a scientific package to store and process the image data as two-dimensional arrays. So to import the NumPy, I imported the NumPy and I stored it as NP. So to import and process the JPEG images to scales in the histogram in my Python package, I use the Pillow module. You will see that there's a package called Pillow here, PIL, that stands for Pillow package. Then later, I use the Scikit image tool. This Scikit image tool, or kit, is used to extend the popular SciPy library to add images processing routines. So specifically, I use the match template function which is what you see here, the match template function. And this match template function is from the scikit image subpackage and used for feature detection so that fast normalized cross correlation of our image can be done during processing. So I'm going to explain what the concepts are. But firstly, at the heart of my program is the match template function. So this match template function is the one that is going to be the major function that is going to run my script. I imported the match template function from the scikit image Python toolkit, and the match template function takes a small template image and finds where it occurs or most closely resembles another larger image, which is accomplished through a process called normalized cross correlation. Cross correlation is a process which calculates how closely related two series of values are, and it's also commonly used for pattern recognition. So in the image analysis, I designated the image file as original and the other as template. So there is an original image and there's a template. The goal is to determine if the image we call template is a subset of the original image. So I performed a quick check to determine if the image template is in fact smaller than the original. Then I determined the size of the image I want to execute so that the match template function will be switched on. So the RMS value that I used is actually a quadratic mean, which is a statistical method for finding the average, and this is going to tell us how close the two images are in terms of closeness to 0. The RMS value of the images are to be considered a match. So if they are close to 0, there is going to be a match. The RMS value of the images are actually calculated and matched against a threshold. You see that I've set some threshold here in line 13. The maximum width is set to 640, maximum height is set to 640, and the RMS threshold is set to 50. So this is why the RMS values of the images are to be considered a match if they are moving close to 0. The RMS value of images are calculated and matched against a threshold. So if the RMS value is very low, then we consider the two images to be a match, and thus the template is considered indeed a subset of the original image. So you observe that in the code, the program is structured as a class. You know, a class is where we always begin our program. I have this class called find subset. So I have a couple of imports that I've made. As I said earlier, I've imported the pillow package, which I referenced as a PIL in line 8. In my line 8 here, I have the pillow package referenced there. And the PIL package in the Python library is going to be used to import the image, and also there's another package called the image chops. See, image chops in line 8 is also imported, and I've also imported the match template function from the SKHI image package and the feature subpackage within the SKHI package. So you can see that I've imported all these in line 9. So I'll move to the method which I call the process queue. There's a method called process queue down my code. This is a method called process queue. What it does is actually performs the image analysis routine. The routine begins by retrieving a pair of images to analyze, which are stored as tuples in the queue. They are stored as tuples in the queue. So the queue contains all the possible combinations of image pairs that we need to analyze. So I'll use the open method in the pillow package to import the two images. So I'm using this open method in line 92 to import the two images. So as I discussed earlier, I designated one of the images as original and the other as template. The template is the potential subset to search for in the original, So I use the path join function. You'll see that the path join function in line 93, 92 and 93, that's the function that I use from the OS module to generate string representing the path to each image for the image open method to use. So after importing the two images, I performed a quick check to verify that the original image is larger than the template image in both X and Y axis. So that is why you will see that there's a verification here to show that. So if the test fails, then we call the analysis, then we can stop the analysis. We can start the analysis of the pairs immediately and proceed on to the next pair in the queue. Otherwise, the program continues on to check if the images need to be resized before performing the match template function. So you will observe that the program compares the width and height of the original image to maximum width and height threshold. So it just compares it to maximum width and height threshold. That is what I have. So when it does that, when it converts to maximum width and height threshold, and there's a constant up here in the program which I have set. As I said earlier, I've compared them to the maximum threshold, and the constant is up here, 640. See them? Maximum height 640, maximum width 640. So going back down in my code, let me put some space here so that the code can show properly. So let me go down to the function. I'm going back to the function. Yes, this is it. So that is the threshold that is set. Now, I chose the value of 640 for both maximum width and height constant because it works reasonably well, as it provides accurate results as the program runs reasonably fast. If either of each of original images is larger than the maximum, then we calculate the ratio by which the image needs to be resized to fall within those limits. So I did this by finding the minimum of either the maximum width value divided by the original image size in the X direction, or the maximum height value divided by the original image size in the Y direction. So you observe that that is what I've done in this function. So when I did that, then I have a ratio, and once I have the ratio, I use the image module resize method to resize both the images of the ratio, that is to resize both images by the same ratio. So the first argument for the resize method is a tuple, actually representing the new dimensions of the image to be resized. And I calculated the new dimension for each image by multiplying the original dimensions by that resizing ratio. I specified the resize method to use the anti-alias resampling filter to revive the best and the highest quality. And I will see that the anti-alias resize filter here in line 101 is used to get the highest quality. So if I did not need to resize the image because they were small enough to begin with, then I set the value of the ratio to 1. And that's why you see that I have the value set to 1 here in my else statement. So once I size it to 1, I did this because we can check later whether or not these images were resized. So after resizing the images, I use the convert method to change them from RGB code images to mode L. So you see that I use the convert method in line 104 to change it from RGB code images to mode L. So then I took those scaled images, then I pass them to the NumPy array function, which converts images into two-dimensional arrays. So I stored them into a new variable. You can see I stored the result into two new variables. So that's what I did there. So when we're talking about the match template function, it takes two input arrays. We want to search, the match template function is going to take two input arrays, which is the original array and the temporary array, which we just created in line 104 and 105 respectively. So let me just go up a little bit. So that is the match template function. So the match template function is going to do exactly that. So if we look at the match template function, as I said earlier, it's taking two parameters. So it's taking two parameters. As it takes these two parameters, it's going to be using them in the subsequent calculation. So after taking two input arrays, talking about the match template function, it takes two input arrays and search the images for a match within. Both of these are formatted as arrays, and the output from the match template function is a two-dimensional array representing the normalized cross correlation of those two input arrays. So the next line is the function on the NumPy array to find the coordinates of the best match from the match template output. So you also see that the argmax function, which I used, is for searching the array and returning the index of the maximum values. So however, the index returned is not a two-dimensional tuple. Instead, it flattens the input array so that the returned index is just a single value. So to convert this flattened index into two-dimensional index, I use the unravel index function, which is used when working with multi-dimensional NumPy arrays. Now that we have the coordinate for the best match location, we go back to the full-size color image and crop out that section for comparison. So if we had previously resized the image, in which case the ratio will be different than 1, we perform a little bit of math to convert that match location coordinates from this resized image back to the original size by using those ratio values. So since the images that were resized, we also need to re-import them so the variable contains the originally sized images. Next, to crop a subsection from that original image, I first converted a NumPy array. Then as an array, I can index out the ranges to keep in both axes. The match location coordinates returned by the match template function, represented by the top left corner of the template image, most closest matches that original image. Thus, I index the original image as an array along each axis, from the match location coordinate on the axis to the match location plus the size of the template image along that axis. So this type of arranged array indexing is useful when working with multidimensional arrays. So after I cropped out the subset of the original image as an array and stored in two variables, I used the image module for array function to convert it back to a color RGB image for use in processing. So you see that this is where I used the conversion talking about the RGB conversion. So it's at this point that I have the subset of the original image, which we think might be the same as the template image. So it's time for us to compare the two. And to calculate the difference between the two images, what I did is that I used a difference function from the image chops module. Image chops actually stands for image channel operation. So the function returns an image, which is the pixel by pixel difference between the two input images. If the input images were nearly identical, then the output from this function should be mostly black image. So what I did next was I took the output from the difference function and called the histogram on it. So you can see that I took the output, then I called the histogram on it. The histogram function is actually called on it. So what I did was now to store the result of the histogram function in a variable called hdiff. This variable called hdiff is called the histogram difference. So when we use the histogram function on RGB color image, what it does is that it will calculate the image for each color separately and then concatenate those results to the output array. So that's what it does. Now, to get the root mean square value, the RMS value from the histogram, what I did was that I summed the squares for every value I calculated in the first line and second line, and I divided that sum of squares by the number of pixels of the image, and it takes the square root of that RMS value. So when calculating the sum of squares, I use the enumerate function on the histogram array, which creates an iterable object which returns tuples with a tuple containing an index and the value for every element in the histogram array. So I used a for loop. You can see that there's a for loop here. So you can see I used the loop after getting the whole thing. Then I use a for loop to process those tuples returned by the iterator and assign the tuple elements to variables for the index and for the values. So for each tuple, I found the square of the color value at that point in the histogram, which is represented by the index. Since the red, green, and blue channels each are 256 elements long and concatenated to the end. So what I did was I used the module operator to get the correct value of each color between 0 and 255. So that's what I did. So after calculating the square for each color value, I multiplied that by the number of pixels in the image that have that color, which is represented by the value of that location in the histogram array. So I put all these inside a sum function, which accumulates all the product and stores the results in the sum of squares variables. So you see that everything is put inside this sum function. So everything is put inside the sum function. So, and everything is now returned as sum of squares variables. So that is what I did at that location. So the size property of the image returns a tuple containing its dimension, and when a tuple is returned, I indexed to multiply those two values to calculate the area for total number of pixels in the image. So finally, I divided that sum of squares value by the number of pixels in the image, and I used the square root function which I imported earlier from the Python math module to get the final RMS value. The last step that I took is to simply compare the RMS values. Sorry. The last step that I took was that I compared the RMS values to a threshold to determine if the difference between the template image and a subset of the original image is small enough to be considered a match. So if the reference is so small, that means the images are so close and they can be said to be a good match. So through testing, I found out that matching images usually have RMS difference value less than 50, while non-matching images have an RMS difference over 100. So I chose 50 as my threshold, which is at the top of the code. So if you look at the threshold that I chose, see that I chose 50 as its threshold. Look at it here on line 15. So that's what I did. So that's why I chose 50 as the threshold. So that when I choose 50, my threshold, which is at the top of the code, can be used. So you can as well tweak this threshold to change the sensitivity of the program to identify the subset matches. So what happens is that if the RMS value that you have calculated is less than the threshold, then we have the pair of images on the GUI, which is processed on the parent queue. So there's a parent queue. So what I did finally was that I used the Python module to build the graphical user interface. As I said earlier, I used the tkinter package to build the GUI. So this is my main function, and you observe that this function is given a constructor. You can see that there's a constructor that starts the whole thing. So this is the constructor to find the subset images. So if I click on the browse button and navigate through the directory containing the images, as I did earlier, I've showed you the images that I want to use and the images that I want to find the subsets within. So it contains 11 images, as you saw earlier. Some are cropped versions of the others, some are similar, some are not cropped versions. And the images which are cropped and flipped versions are also shown. So those images that are cropped and flipped are given a variety of permutations to search through. So if you look at the subset image button, you will see that this is where we want to find this. This is class that is going to give us the subset, and the status bar is going to be updated so we can know which pair of images has finished analyzing and how many pairs of images remain to be analyzed. So the progress bar that I used as I'm going to run the code is going to be incremented to determine the percentage of the analysis that has been completed. So as the subset images are found, the GUI, the graphical user interface, will populate the table to list the pairs of images and specify which of the original image. It will specify which one is the original image and which one is the cropped version of the original image. So after the program has run successfully, the cropped version of the image will be analyzed, and all the images will be finished. And once they are finished analyzing all possible image pairs, the status bar will now display done and let you know how long it took to perform the entire task. So I'll go to the part that's going to show us how I built the GUI. So this is where I built the GUI. I'm not going to talk about the GUI now because it's going to be a long story. GUI is a common graphical user interface that we use tkinter to build in Python. So this is the part that is talking about the GUI. So I'll run the code. If I click the run button, that will take some seconds for my code to prop up. So I'll wait for that. Okay, it's coming up. You can see the Python sign here. Okay, the GUI has showed up. So you can see that it's giving me the path of the images, meaning that it's already showing me that there is an image folder here. So it's giving me the path by default. But if I click on find subset images, it's going to tell me that nothing has been chosen. Let me click that. You see, it says invalid search directory meaning that this directory is not valid. So that is the way we have written our code, as you have seen earlier down. So I will need to now browse a real path so that my image can be shown. So let me browse. If I click browse, it is going to search for my directories on my desktop. So I'll click on my desktop. When I click on it, it takes me to all the directories. And here, this is the image analysis 1 folder that is my working directory. So I'll click on it. It shows me the image analysis. So this is the folder that I am presently. So if I click find subset images, it says need at least 2 images to analyze, because I have not specified a folder that contains images. So you will observe that here, right here, there is no image. So I'll need to browse again so that I'll navigate to the folder. Now I'm inside my image analysis 1 folder. So I'll need to click on images to expose the images now. So the images have been exposed and they have been put inside that directory. So there's a path, there is a real path now for the analysis to begin. So I'll click find subset images so that the subset can be found and the analysis can begin. So I'll click that. You see that it says analyze Caribbean JPEG versus 477.97145.jpg and Caribbean JPEG pairs remaining. So it's telling us that the progress has begun. So for now, my progress bar is taking some time to load. I'll need to go through my code again to fix some bugs as the GUI needs to be updated. Hopefully in the next video, I would have fixed these bugs. For now, we have our GUI working to analyze the images, which is a great achievement. Please watch out for the next video in my channel so that I will have solved this problem. Hopefully. Learning never stops. So thank you for watching and goodbye for now. Thank you.